Hey folks, welcome to this episode on covalent bonding and properties. So covalent bonds happen between two non-metallic elements. They have similar electronegativity in that they have a high electronegativity and they also have high ionization energy. That means they do want to gain electrons and they don't want to lose. No losing. Okay? They do this to achieve, again, their octet, which we spoke about before, that full outer shell. But because none of them want to lose and both of them want to gain, okay, none of them lose and gain, what they are going to end up doing is they're going to share electron pairs between the bonding atoms. And this is there's an electromagnetic attraction between the positive nucleus and those bonding pairs of electrons. And this, ladies and gentlemen, is our covalent bond. So let's look at chlorine. Here we'll have two atoms of chlorine, Cl and Cl. Okay, and if we look, it's in group number 7, so we're going to have 1, 2, 3, 4, 5, 6, 7 electrons. And again, we have 1, 2, 3, 4, 5, 6, and 7 electrons. Now, in this case, what we're going to see is that chlorine has an unpaired electron here and an unpaired electron here. They do want to get their octets, and the only way that they're going to be able to do this is by sharing those two electrons. Remember, both of them have the same electronegativity and they have the same ionization energy. Neither of them want to lose, both of them want to gain. So what we're going to see is we have chlorine and chlorine, and I'm just going to have chlorine here, 1, 2, 3, 4, 5, 6, and 7. And this chlorine, let me just erase that one there. I'm going to put that one in the middle there. And this chlorine over here will have 1, 2, 3, 4, 5, 6, 7. So what you can notice is that chlorine ends up sharing these electrons. These are our bonding electron pairs, or bonding pair of electrons. Okay, so you can see that at the same time, what you'll notice is that this chlorine atom over here has a full octet. Okay? It has 2, 4, 6, and 8. At the same time, this other chlorine atom also has a full octet. Okay, as you can see, spelled that wrong. Okay, as you can see, it has 2, 4, 6, 8. So by sharing these electrons over here, both are satisfying their octet, both are stable, both are very, very happy. The most simple types of molecular covalent bonds come in the form of diatomic molecules. And these are, in our sense, diatomic really means just two atoms. But we usually apply this definition into atoms of the same species. Now, you may have seen this mnemonic before, Hofbrinkel, which is all about the types of elements that form diatomic molecules, bonds between themselves. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So all of these will form diatomic molecules, for example, H2 or O2, F2, etc., etc., etc. And they all do this by sharing the electrons, that bonding pair of electrons. Now what you can see at the bottom here is there's a little bit of a difference. For example, chlorine needs 8 to have its full outer shell, so you'll see that it has 7 already, and it shares those 2 other electrons, while hydrogen only needs 2. It already has that 1 valence electron, and it satisfies that kind of duet, if you will. So now, what about oxygen? Well, let's look at oxygen. We have oxygen here, and let's see how these end up bonding with one another. 1, 2, 3, 4, 5, 6. Again, 6 because it is in group number 6. Now what we can see right from the get-go is that they have 2 unpaired electrons. So let's pair these up. We have this pair, and let's redraw it. So we have oxygen and oxygen. It's going to be sharing 2 pairs of electrons. So we'll put that in the middle, 1, 2, 1, 2. And again, it still has these unpaired electrons on here and here. So we'll draw those in 1, 2, 1, 2, 1, 2, 1, 2. Now if you're wondering why I draw this, it's just because the electrons try to repel each other and they try to create the most amount of space between themselves. This is something called VSEPR, and you'll learn about this a little bit later. But let's go back to our oxygen here and let's see what's actually happening. And so what we see is that we have these 2 pairs of electrons which are being shared. Again, these are our bonding electrons. And then here we have 2 pairs on this side, and these are called our non-bonding electrons. Also, they're called lone pairs. Okay, they're not involved in the bonding. But what we can see is that by doing the sharing of the two pairs of electrons, each one of them has an octet, 2, 4, 6, 8. And again, we have 2, 4, 6, 8. So both of these have a full outer shell. Now to redraw this, what you most likely see is this right here. We'll still have our two lone pairs. Okay. But what you'll typically see is that you'll have this kind of short form, and that right there is called a double bond. So oxygen shares its electrons with another oxygen atom to form a diatomic molecule, and it does this by creating a double bond. Okay. So here's a little diagram of our polyatomic ions. The first ones over here are really our diatomic molecules. They're the simple ones. You can see that hydrogen, fluorine, chlorine, bromine, iodine, they all form single bonds. But nitrogen actually forms a triple bond, and oxygen forms a double bond. Now we also see some polyatomic molecules that exist in nature. Phosphorus kind of bonds with itself 4 times, and sulfur 8 times. There are a whole bunch of different covalent structures. There's really two main types. There are simple molecules or discrete molecules where they have a specific amount of atoms. In this case, we have CO2, where we have 2 oxygen atoms and 1 carbon atom. And as you can see, they're actually doubly bonded to one another. And we're going to be learning how to draw these structures in a bit. But what you can also see are these types of structures here and here, where they're not discrete molecules. These are actually just tidbits. These keep going in all different types of directions. And what we see, these are giant structures that are not molecules. These are molecules. Once they have all the atoms in a certain configuration, well, you're going to have to create a brand new molecule if you want to make something else like this. With these, they're a giant structure. They can keep going, and they're not really limited by size. Now, this is an interesting one over here. This is a diamond thread, and these are considered as the forerunners in creating the space elevator. So unlike ionic compounds that have a formula units, covalent molecules have a molecular formula. Again, these are when we're talking about discrete molecules that have a certain amount of atoms and that have a certain amount of size. And again, this molecular formula gives the specific and the exact number of atoms in each element in that compound. So for example, in this molecule here, we have 1 carbon flanked by 4 hydrogen atoms, and we get CH4, the common name being methane. Now, when it comes to the types of bonds, we actually have 2 main types of covalent bonds. We have polar and we have nonpolar, and it all has to deal with the electronegativity between bonding atoms. So even though atoms might be involved in a covalent bond and they're sharing electrons, we have to look a little bit further and see, are they sharing it evenly or not? Now, if they have a similar electronegativity, they're going to be sharing those electrons very evenly. As you can see here, chlorine, we have 2 atoms of chlorine, and because they have the same electronegativity, there's the same atom, they should have the same amount of electronegativity, those electrons are found right in the middle. So there's no more negativity on one side or the other, they're shared equally in the middle. We have a different type of covalent bond, however, is that when we start having a little bit of a difference in electronegativity between the atoms. Now, in this time, when you were looking at electronegativity, you know that chlorine has a higher electronegativity than hydrogen. What this means is that chlorine will be pulling the bonded pairs of electrons closer to itself. It's going to be moving them over here. Now, one thing you have to remember are, what is the charge of these electrons? They're negative. Well, if these electrons are moving closer to chlorine, these ones right here, if they're moving closer to chlorine, it's going to make this space around chlorine a lot more negative than the space around hydrogen. And it's kind of shown by the magnitude of this arrow. And as we can see here, the arrow is the same size, the pull is the same, and so the electrons are found in the middle. In this case, the electrons are going to be pulled closer to chlorine, making this side a little bit more negative. Now, it's not transferring the electrons. It's still sharing, so that side is only going to be slightly negative. It's not going to be a full positive or negative like we see in cations and anions. Because these electrons are going to be coming closer to this side, it's going to make this side slightly more negative, and we use the symbol slightly negative. Because the electrons are being pulled away from hydrogen, it's going to make this side slightly more positive, and we have slightly positive. And this type of bonding is called polar covalent, because we are creating a dipole. The last one is not really part of covalent, but just to give you as a reference, ionic bonding, there's a huge difference in electronegativity, and there's going to be a transfer of electrons. So sodium is just going to give its electron up to chlorine. It's going to have a full positive charge because it just completely lost an electron. Chlorine's going to have full negative charge because it just completely gained another electron. And again, there's going to be attraction between here. When we look at electronegativity differences, we know that we can find them on the periodic table based on the Pauling scale. So it goes 4, 3.5, 3, 2.52, and similar over here. One thing for you guys, you need to remember these electronegativities. These over here, and at least these ones over here, as well as the electronegativity for hydrogen. So that should be put into memory. If you need any other ones, I will give it to you. But how we can find that electronegativity difference is just by looking at the bond. So let's say, for example, we have a nitrogen-oxygen bond. Okay, so what we're going to find is to find the differences in electronegativity, we first find the electronegativities. The electronegativity for nitrogen is 3 and oxygen is 3.5. Now we're always going to subtract the smaller value from the larger one, so we'll get 3.5 minus 3, and we'll get 0.5. Now that value will tell you, or give you an idea at least, as to what kind of bond is going to be formed. So again, non-polar covalent, or sometimes called pure, is all about sharing the electrons equally. And there's a nice little picture here, diagram, where we have this kind of tug of rope. They're both the same strength individuals. They're going to be pulling those electrons the same, and the electrons are going to be shared in between themselves. However, when we talk about polar covalent, the electrons are not shared evenly because they have larger differences in electronegativity. Chlorine really wants those electrons because, again, it has a high electronegativity. Remember, that's because it has more protons. It has a higher nuclear charge than something like hydrogen, and it's going to pull those electrons closer to itself. Now, what that's going to make, this side is going to make it slightly negative, and this side, the side that the electrons are being pulled away from, are going to be slightly positive. And that results in a charge differential around the molecule, which we call a pole. So we have this little bonding continuum to help you visualize what types of bonds might be created. And we can see from about 0 to 0.5 here, we create this nonpolar bond. Again, this is talking about differences in electronegativity. So once we do our x minus y calculation, we'll get a value. We apply this value onto this table to see where it sits, and that will tell us an idea of where, what kind of bond is going to be formed. So again, from 0 to 0.5 is nonpolar. They're going to be sharing the electrons evenly. From about 0.5 to just under 2 is going to be this polar covalent bond. Now you see this kind of grid here where it goes from 1.6 to 2.0. We'll talk about that in a second. Any difference that's between 2 and 4 is going to be for sure an ionic bond. But there's this little gap here, and this has to deal with it's a little bit of a kind of a little unsure zone, if you will. It all depends on what things are going to be bonded. If there's a metal and a non-metal bonded and it falls into this range about 1.6 to 2.0, it's going to be considered ionic. But what you'll find is when you have some non-metals bonding together, we have non-metal and a non-metal, that will still be kind of in a polar covalent section. So it's a little bit of a gray zone here. If you get into this gray zone with your difference in electronegativity and you have a metal bonding with a non-metal, it most likely will be ionic. And if you have a non-metal bonding to a non-metal, again, you're in this kind of range of 1.6 to 2.0, it most likely will be polar covalent. Covalent structures, there's two of them like we were mentioning. There's molecular covalent, which has discrete amounts of atoms. So for example, if we have like H2O, we'll have H, O, and H. And that's the size of the molecule. It's not going to get any bigger, any smaller. You'll need another molecule if you want some more water. But for example, if we look at giant covalent, we can look at a diamond, which we have 4 carbon atoms that are bonded to one another. And these 4 carbon atoms, here's our little bonds, they can bond to other carbon atoms, and et cetera, and et cetera, and et cetera. Okay, so these can keep growing, keep growing, keep growing. And if we're talking about a diamond, that's a pretty big diamond and wonderful. But these have no maximum size. And they have every single bond is a covalent bond. The main difference is that these molecules, inside of the molecules themselves, These are covalent bonds. However, if we have another molecule of water, it will interact with another molecule of water using something called intermolecular forces, which are much, much, much weaker. Here are just some diagrams of our two types. Here we can see simple molecules. You can see that they're discrete sizes. They have a certain amount of atoms. Here we have our giant covalent networks that are massive and can keep growing, and they're not limited by atoms. Here we have some properties of the covalent compounds. You can see that they're starkly different. These molecules have low melting points, while these ones have high. These are poor conductors. These are very poor conductors, so same kind of thing. In the structure, they're discrete molecules, and they can form a crystalline structure, for example, iodine. And I'll show you that in class. Versus a giant covalent structure, it just keeps growing. It's not limited by size. So again, to form covalent bonds, it has to deal with atoms that have high ionization energies and high electronegativities, and these are usually characteristics of nonmetals. Because they don't want to lose and they both want to gain, they're going to have to share electrons to create that octet. So here's our final summary of our properties. I really suggest you print this one out and keep this in your books. It's a nice little reference form for later studies. And again, a nice little graphic for our intermolecular forces, our intra, and interactions with water, for example. That's it for this episode. Thanks for watching. See you next time.